What we'll do is we'll first go to the website. As always, start with intro to bioinformatics.com. How'd you like the website, by the way? It's okay?
Yeah.
It's serving your purpose so far? All right. No problem with the materials and accessing everything, right? Okay, that's good. All of it free. No money paid. Except for the domain name. All right. Yeah. Okay, so let's go to our functions and apply. So under your course details, go to our functions and apply. Click that. And it should say code for practical over there. So you download that file. The file is called apply.r.txt. Show that file in Finder and copy it to your folder wherever you have your course folder on your local machine. At that point, you rename that file by either right-clicking or just gentle click with one on the file name. Use the .r extension. Remove the .txt. So it'll become apply.r instead of apply.r.txt. Is that okay? And then use R. Use that. Now you open that with RStudio. Is everybody there? Perfect. So the first thing we're going to do is we're just going to click on this to see the definition of lapply. So Command Enter if you forgot. Put the cursor on that line, do Command Enter, and you should be able to get this definition of apply, which tells you, lapply, which tells you it takes two arguments, x and another function, and ... So again, ... is one important thing that I just realized that to clarify things would be useful is to notice that ... is only used during definition of the function. At runtime, you cannot say ... as a user when you're running a function on your console. Does that make sense? Because at runtime, you actually are going to give definitive arguments to the function. It's only when you're defining a function, when you're writing the code for the function as a programmer, you don't know what the user is going to give as other arguments. But when you are executing, you are in fact the user of that code. And therefore, you know what function you're calling and what arguments it's taking. So there is no need for ... at that point. Is that clear? Okay. So let's execute the next line. What's happening in the next line? I'm doing a screen. So if you see in the next line, we're creating a list. Can somebody tell me what kind of list this is? Just go and run that code and tell me what kind of list this is. Anyone? Before I start picking on people.
Numeric?
Well, list can be of, yes, one of the elements is numeric. Which element is that, Linda? Well, actually, A is the numeric. Well, I mean, this is more of a real numbers, but yeah, technically they're both, they're all numbers. A is the first element, which is an element of integers, and this is defined as 1:5. It's a vector. And B is a vector of random normals with, you just give one argument, so that's the random normal 10. So we're saying just create a random normal of 10 numbers with mean 0, standard deviation 1. If you're ever confused, just always, you can type out what our norm is, and it gives you the description here. So by default, see, the definitions here will make more sense now that you understand functions. The default value of mean is 0. That means that if you don't specify any other argument, here when you say our norm of 10, we're saying that we're just saying this first value is n, which is the number of observations that you want the random normal for. By default, the mean will be 0 and standard deviation is 1. Okay? Does that make sense? All right. So we call that here. And so X is a list which has two elements, A and B. The first one is a vector. The second one is a random normal 10. Now we're finding the mean. When we do lapply, what happens in this statement? What is happening? Without executing, tell me what is happening here. Anyone, take a guess.
You're gonna apply the mean function to the list X.
That's very good. Now, what do you mean by applying the function to the list X?
Meaning it'll take the mean of both elements of that A and B.
So you mean the element A of the list is in fact a vector A.
Okay, yeah.
And the element B is in fact a vector of random normal numbers.
Yeah,
random numbers.
Yeah.
So what will it do now? It'll take the mean of A and B together, or it'll take the mean of A, display it, and then take the mean of B and display it.
I thought it was the latter, but now I'm confused.
No, you're right. It is the latter.
Okay.
So here's what happens. It creates, it takes and applies to each element of the list. It applies the function. That's what lapply does. So you get the mean for the first vector A and the second vector B, and that's what you get. Okay? All right. So the next one. What are we doing here? Just explain the statement. We're creating a list with how many elements?
4.
Yes. Are the elements named? Yes. They're named A, B, C, and D. What is the first vector of that list? A. What is the values of that?
1 to 4.
1 to 4. For B, what is B in the list X?
10 random,
Perfect. What is C?
20 random numbers with a mean of 1.
Perfect. So 20 random numbers with the mean of 1. So by default, the first value is the number of random numbers you want to generate, and random normal numbers, and then the second value is the mean. And what is D? Is a list of what? 100 random numbers with a mean of 5. Perfect. All right. So let's see X. I mean, basically, it's gonna show the elements C, A, B, C, D, as we discussed, and we're just applying to each element of X the mean. Now, does lapply now make sense to everyone? How about we change the code a little bit and try to see if we can, what other function would you like to apply to that list X? Choose your function and apply. Like, just pick another function instead of mean. So, right here, there are 4 elements. Let's say instead of mean, we wanted to apply another function. Can you give me your favorite function? Sum is another function. Yes, that's one. How about we choose range? Okay? Let's see what happens now. So now, when we apply the range function, for A, you get the range 1, 4. You get, for each list, you don't just get one value in that list, you get a vector in each list. So you have 2, 1 and 4, minus 2.4 to plus 1.08. Okay? Anyways. Okay, so next. How about we create another vector, 1, 4, and try to apply the uniform distribution function to that. So it takes 1, 4 and applies and returns this values. Does this make sense? The uniform distribution function takes n as input, which is the number of observations that you want to generate. So here, the number of observations is different for it. First it's 1 observation, then it's 2 observations, then it's 3, then it's 4. And then you're just basically calling, this is equivalent to calling list runif1, runif2, runif3, runif4. Do you agree? It's kind of like that's exactly what you got, except the numbers are different, but with this. All right? Okay. Next statement, 1, 4. Now this is where the ... comes into play. I'm so glad there's an example. Do you notice? Here you just called runif, right? But you didn't have any arguments for runif. That's what I was trying to explain. I should have just looked here. So x is 1 to 4. But now you want to call runif, but you want to specify the arguments for runif with minimum argument as 0 and maximum argument as 10. If it wasn't for the ... you would not be able to give these two arguments here. Right? So now when you call runif, you apply this and call runif, you have each of these with a minimum of 0. So none of these arguments are going to be less than 0. Okay? And then the maximum is 10. So that is the whole point of ... Right? Because you did not know when you were writing the lapply function whether you're going to call runif here, or you're going to call range here, or you're going to call other function mean here. You don't know that. So you have to put ... meaning that there are other arguments that could be passed to this function which could change based on the user input. Okay? By the end of this class, you'll all know ... really well. Okay, moving on. What is happening here? Anyone in this statement? Sorry, this one. Go ahead.
Prints the table.
Now, what are we doing here? What are we creating? What does the statement do?
2 mapping.
Yes, 2 matrices, but what? As
1 to A, matrix A has 1 to 4 with 2 rows and 2 columns.
yes,
Matrix B is like 1 row, 6 columns.
it's actually
three rows, 2 columns.
Right.
With values of 1 to 6.
And then what is the purpose of the list around it? So what we're doing essentially is what? We're creating a list of
2 matrices.
There you go. So if you print X, this is what you get. All right? Okay. Now what are we doing here? We went through this in class, but let's go over it again. What is happening now to that list of matrices that we've created? Shall I pick on people?
You're applying an anonymous function defined below. It just spits out the first column.
Perfect. Nicole, you should thank Linda. I was going to pick on you. Okay, lapply on X, the function ELT, the function which takes us the element and returns the first column of that element. In this case, the element variable would be replaced by the elements of the list, which are matrices, and therefore it'll return two answers for list the element A and element B, the first column of each. Now, You could also just define this. This is the way to define it anonymously as part of the apply, but this is a little simpler way of defining the same exact thing. So I don't know why this is after. I would have basically done this before and then explained to you anonymous functions. I guess that I'll keep that in mind for next time. But here we're creating a function f, and this is essentially that anonymous function that we've defined here, where we're saying take the input ELT or element and return the first column of that element matrix, or whatever element is there, as long as there's a 1. Does that make sense? And then now you're applying x. On x, you're applying this function f. Okay? Okay. So that's what you get, 1, 2, and 1, 2, 3. One interesting thing to do would be to, let's define A, in fact, as as just a vector, and B is also just as a vector. All right. Okay. So instead of a matrix, now we have an error. Oh, here. Okay, so what is x now? It's just 2 vectors, right? Now if we call this lapply x on f, what will happen? Alright, I'm going to start picking unless somebody saves the day. It's going to be the superhero. Marcus, what's going to happen?
So we're on line 36.
Line 30, well, I mean, my lines may be different than yours, but basically we just changed, if this is x, x is defined here, it's a list containing 2 vectors, a and b.
Okay.
A is 1, 2, 3, 4, and b is 1, 2, 3, 4, 5, 6. And we're calling on a, we're calling this function f, where f returns the first column like this. This is the function f. What?
F is going to be applied to both A and B.
Right.
And it's going to return the first column, so it's just going to return 1 and then 1.
Okay.
Is that it? Those are just rows, so the first column would be 1.
Incorrect number of dimensions. Because for every vector, you don't have a dimension comma 1. The way you're thinking, if we remove the comma and redefine this as just ELT1, then you will get what you're saying 1 and 1. Okay? So just a subtle difference. Something to, think about. Okay? Alright. So moving on. Let's see what's the next thing here. We have x as a A, B, C, and D. I'll apply x comma mean. X is this. We apply the mean. And this is our mean. Now, the interesting thing here is now if we do sapply instead of lapply. So each element here is one number. So sapply does what?
Simplifies.
Perfect. S for simple, therefore sapply. It simplifies what? Simplifies lapply. So it's everything else the same as lapply except it simplifies the output if it can. Now it'll return a vector. Simple. Instead of a list. This lapply always takes a list, returns a list. L for list. Lapply takes a list, returns a list. Sapply simplifies lapply. Therefore, returns a simple, possible. Okay?
Does it coerce the elements?
Yes. So this is where we come to split. This is your split is a function. It takes x, f, and drop is equal to false. I'd like you to okay, so I guess we can go over this. So let's say x is this. X is a vector which has Wait, is X a vector? Yeah, X is a vector. It contains 30 elements. 10 random numbers, 10 uniforms, and 10 random numbers, normal distributions with 10 and 1. 10 with 1 mean. Okay, now F is repetition with 3 of each. It's factors. So 1, 2, and 3 are the levels. And then GL is a function that repeats the number of times. So 3, you have 3 levels. The number of times you want those levels is 10. So it by default chooses 1, 2, and 3 and repeats them 10 times each. Okay, that's what the GL function does. Now if we call split x comma f, you split those into 3 parts. It creates a list and you split them each. So you just split a vector and made it into a list. Okay, that's all it did. So the first 10 elements became the list, the first element. The second 10 elements became the second element of that list, and the third became the 3. That's all split function does. It takes a vector, splits it into a list based on the factors that we have. Does that make sense?
There was no repeating.
In what? There's no need to repeat. What you're doing here is you're just passing a vector or a factor vector which tells you what type it is. So the first 10 are of type 1, the next 10 are of type 2, and the next 3 are of type 3. So you just split them into 3 lists. The type 1 elements are here, the type 2 elements are here, and the type 3 elements are here. Where this is x, right? So we define x as a combination, a vector of 3 different kinds of distributions. First is a random normal with mean 10. The second is a uniform with mean 10. And third is a random normal with mean 10, but with 10 numbers but mean 1. Sorry. And so R norm 10, R uniform 10, R norm 10, comma 1. You know what that means, right? So now you have 3 different elements, but now the problem comes when you want to split them, because in a vector they're all one vector, right? So if you wanted to split them, a simple way is to define a factor of what is what, and then just go split. Don't ask me why this is useful. Sometimes it's useful. All right.
So can I
Yes.
make sure I'm understanding this? So a vector, you can tell it apart from a matrix from the previous question you had asked. When it wasn't returning a column was because
It is
you
unidimensional.
always have to have this indexing on the row side and a column. When you don't show indexing across the top, across the columns, then it's a vector, right? Because vectors only do the row.
Vectors has only one dimension. It means that it's a string or whatever.
It can be row.
It will only be rows.
Just one dimension.
Vector is just row. A row of elements is a vector. That's it. A matrix has 2 dimensions. So matrix can be thought of as a combination of vectors where each vector is a row.
But you can have
Or a column-wise vectors. But in essence, when you display those columns, they'll still be displayed as rows. The values.
It will have a labeling across the top.
Which one? Oh, those are different. The labeling you can just control by saying names. So even a vector can have names. So let's say I create a vector with let's say x is 1:3, and then I say names of x, and I'll just say Linda, Nicole, and Sue. So now if I display x, this is what I get. Those are just your names. Okay? Does that make sense? There's nothing to do with that names are specific just to matrices or to others.
Then to determine if it's a vector or not, is there like a type a class?
Yeah.
And it will tell you what it is.
I mean,
It seems like you could get easily confused if you don't realize what the set you're working with is.
well, I mean, it's an integer class per se, but as long as it doesn't have a... So here's the way I do it. If you say dim of x and you get null, that means it's unidimensional. But if you do length of x, you will get the length of the elements in there.
Okay.
So dimension is only applicable to
2D.
something that has more than one dimension. If it's one dimensional, then length. Okay. So, oh yeah, so there you go. So the use for split now is supposing you have a vector and you want to apply something to just the elements which are of a particular kind. So the way you can do that is you can create, so x is our vector which has 3 different kinds of elements. We split it and then we can apply that split on that split the mean. So now it'll calculate the mean of just the 1 type, the 2 type, and the 3 type. Does that make sense? So say you just had a so if you're with me, can you tell me what's going on here? Anyone in this statement? The one highlighted.
You're just creating a vector with 3 elements.
There three
Or
three kinds of elements.
Yeah.
But what's the total number of elements?
Oh, I guess 30?
Yes. So the first 10 are random normals.
Then uniform and then normal.
Yes, but with mean
With a
1.
mean of 1.
So now you want to try to calculate, let's say this is our vector, right? Our final goal is to find the mean of each of these elements. But because it's a vector, they're all concatenated with one next to each other, right? So this is your vector. It has all these elements as in one row, even though they're displayed like this. That's because of lack of space. If I just did this, you'll see. Okay? So they're all, this is x, right? Now supposing I wanted to find out the mean of the first 10, then the next 10, and the next 10, it's very hard to do, right? So how do I do that? Then I can, so the first thing I need to do is create a factor class which can split them into 3 parts, right? I have to define something that will split them. This is f. F is a factor variable that says the first 10 elements are of type 1, the second 10 elements are of type 2, and the next 10 elements are of type 3. So just randomly assigning them a type. You know, you could have just as well, instead of f, you could have just said f is repeat men, comma 10, and here. You can create a vector of this type. Repeat women, comma 10, and then, so GL function just helps you do that very fast, and just neutral as 10.
So if the number of elements, say for like our norm, doesn't match the number of elements.
Yes, then it'll be an error. So let's try that. Actually, instead of m, let's just do, say, of type 1,
Then you can't use a GL function. Is that
2, and 3. So instead of 10, let's just say 11. All right. Now if you do this, well, it still split it. It just gave you a warning.
So it omitted the 11th one?
Possibly yes. It just gave you a warning instead. And so. Yeah. And actually, what it does is it keeps assigning them. So here you get 9, 10, 11. The next 11 go here. And for the third one, it just removes it only goes till 9 because 10 and 11 are already taken here. Does that make sense? See what happened here? Or no? So because you said that the factor has 11 values for 1, 11 values for 2, and 11 values for 3, when it was trying to do the split, it took the first 11 values and assigned them a type 1. It took the next 11 values and assigned it a type 2, leaving only 1, 2, 3, 4, 5, 6, 7, 8 values for the remaining type 3.
So even though you wanted to specify 10 elements, it just did that.
Well, because it only encountered the error in the last last set of 11 elements. It didn't find the 11 factors. It only found 8. Does that make sense? Okay. So now if you try to do the split, it'll still do the split. It'll give you a mean, of each, except it will say again that f has 11 if it's not a multiple of the split variable. So it gave you the mean for the remaining classes. The remaining 11 elements here, 11 elements here, and then 8 elements here. Okay? Does that make sense? Okay, moving on. Are you doing all this with me, or you want to do it later? I guess you'll do it later on your own.
I'm trying to do it with you.
Okay, cool. Stay with me. So this our standard data set. So you have the air quality. We just loaded the air quality data set. You know, if you do a head on it, you see that it has ozone, solar, wind, temperature, month, day. Now the important thing here is that to understand that the functionality of split, it helps you split the air quality with the variable month. So you see what I'm saying? So the month column in this data frame, let's do a summary on air quality. Quality dollar. Okay, so, or even better, if you just see what are the elements of air quality dollar month, it's a factor variable. It has month 5, 6, 7, 8, and 9. So it goes from May till September, and it basically the entire data set is for the 5 months, and you're measuring air quality on those 5 months. Okay, every day on those 5 months, or you get the air quality. All right. So what we want to do is split the air quality data frame based by the month that it is. Okay. So we split. So where are you lost? Tell me. Split is a variable that helps you split your vectors or data frames based on a factor variable. Remember we covered factors a while ago, which tells you what types things can be. So say month May is of type 5, June is assigned a value 6. So when you're saying each day in that month, it's you're assigning it a factor corresponding to that day. So all days in May will be called of type 5. All days in June are of type 6. Okay? So now you want to split your data frame based on the the month. Okay, so now if you do string s, it basically tells you, it's a list. So it returns a list, and in that list is a data frame of 31 observations, where the first observation for ozone in that month is these are the values. Okay, I know it is not a pleasing display, but here this makes it better. I mean, so ozone, it has solar.r, wind. So all of those elements that you had for the original data frame are still there, except now they're split up by month. That's all just happened with the split variable. Okay? So what happens next now? We can now apply on S, which is our split list, a function x, which calculates the means for ozone, solar, and wind. Do you see what this function is doing? Right here. This is an anonymous function which is returning the means for the columns ozone, solar, and wind for that list. Now, so we split up the data frame first by month, then we're trying to find the mean for these columns in that month. That's all that's happening here. And using lapply, it becomes a one-line statement. Remember the point where I said R is really dense? This is that dense part. You have to go through each thing step by step to understand what is happening. Everything is packed within something else. So now we do that. Oh, sorry. I didn't complete the function. So this is where the function is completed. And so now, for the month 5, for the month of May, this is your ozone levels, this is your solar, and this is your wind. Now notice that we didn't remove the NAs. Therefore, when you have an NA in a vector and you calculate the mean of that vector, it'll give you NA. Okay? So for the others, the ones that did not have any NAs, you got the values for their particular things. So similarly, if you do an sapply on that, it'll simplify things and create a anybody. Close. Each of these list outputs has 3 elements each. When you're trying to simplify them, I'm pretty sure Linda knows the answer.
Matrix?
There you go. So it creates a matrix with 5 columns based on the month, because you have 5 elements here, and for each row you have the values for that that variable, which is ozone in that month. Okay, so it's simplified into that. Similarly, now due to at runtime we decide that we want to remove the RM. When we are passing na.rm here, we're using the ... functionality to pass extra arguments to sapply, thereby removing the RM, the NAs that we have here. Okay, so that's why we had ... Do that, and voila, we get a much better matrix. All the NAs removed. This makes perfect sense now. Okay. All right. What would happen if we had lapply here? It would just give us a list, but na.rm still works because it's being passed on further to remove the RMs as an argument to lapply. Okay? So here's the difference between sapply and lapply. Essentially, it simplifies it. One simplifies it, creates a matrix. The other one just gives you a list. Lapply, list always output. Okay? All right. Moving on. How much is left? Quite a bit. Well, you probably have to go through it, most of this on your own. We just have a couple of more minutes, but let's do this set of code. X is R norm with 10 values. F1 is a factor for 2 values, repeated 5 times each. F2 is another with 5 values repeated 2 times each. That's F2. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Does that make sense? Okay. Now we try to create and call the interaction functions with these 2 factors. I think you have to go and look up what an interaction function is. There are lots of these kind of interaction is one of those functions. You just have to compute factor interactions. If some of it seems too complex for you, you can just leave it. It's fine. You're not going to probably need to use this. This is more of an advanced sort of concept to, frankly, I haven't used factor interactions forever, and I've been using R now for more than 6 to 8 years. Okay. But you can look at it. It's essentially, as the definition says here, interaction computes a factor which represents the interaction of given factors. The result of interaction is always unordered. So right here, you have 1 and 1 is common, 1 and 1 here, and then now you have 1, 2, 1, 2, 1, 3, 2, 3, 2, 4, like that. So there are 10 interactions between these 10 factors for each, between these 5 factors. Sorry, between these 10 values of F1 and 10 values of F2. All right, so 1.1, 1.1, then 1.2, 1.2, then 1.3. Oh, sorry, 2.1. So it's going the other way around, right?
So is it like a distributive type of thing?
Kinda. It's just trying to combine the 2 into 1, right? So there's 10 values based on these interactions. So 2.5 is the last one. So this, and this is going like this: 2.5, 2.5, 2.4, 2.4. Like that. All right, so one with the other. So you're basically creating a joint factor between the 2, and then here again you're trying to cause a split of X, which is a 10 based on this list of F1 and F2. So this is what it does. It creates a list of 10 where the first element is these two numbers, because they're of type 1.1 and 1.1. All right. So those two are based on the value of x, which you have here. Let me know if this is still not confusing enough. So notice that you've now split based on the joint interaction between two factors, f.1 and f.2. Sorry, f1 and f2. So the joint interaction creates these two of type 1.1. So that 1.1 is these two values of x, 0.937 and 0.48. Okay? The next value is of type 2.1. Notice that none of those specify that criteria. They're not of that type, so therefore it's num0. And then the next is 1.2. The 1.2 interaction specifies numbers minus 2.1 and minus 1.03. So these two are of those type. Okay? Just trying to tell you that if you have instead of one, if you weren't confused with one factor, here's the interaction of two factors. That said, you will probably not use this, so we're going to just ignore this for now. And we go straight away to simulate some data where you're trying to create the, use the t-apply. So let's simplify things a little. Let's go over to x, which is a 30 values based on this. F is a simple one factor now. See, now you appreciate the one level factor instead of having factor interactions. You just have one factor with three different types, and you just do a simple t-apply on one kind of factor and find the mean of those. So all the type 1s have a mean this, type 2s have a mean this, type 3 have a mean this. Okay, simple enough, t-apply. If you do simplify as false, then it returns a list. If you have simplify as true, by default it's true, so it returns a vector. Okay? So like I said, t-apply should be v-apply, vector apply. It returns a vector by default. If you say simplify as false, otherwise it's very similar to any of the other applies. Okay? It just needs this factor f index what to do what with what. We're just a little bit left. Let's create a matrix. Now we want to apply the mean of each column. So we say apply mean to each column by saying number 2. We want a sum of each row. So we apply 1 to the apply to that matrix X and specify 1 and then say sum. That's how you use apply. Okay? Remember, apply is for the margins to either rows or columns of matrix is the most commonly used way.
Margins? What do you mean? Just
The margins will be like, basically either the rows, all the rows. For each row, you want to find so that would be the margin this way. So you have the rows, or you have to each column, that would be this margin on the matrix.
And when I think about a margin and a matrix, I just think about the top row. Is it just the top, or could it be any row?
When you specify, so here you're specifying 1 for all the rows.
Okay.
So that means apply this function to each row. And when you say 2, you're saying apply this to each column. So the margin is a generic term that is used to specify that it is used on either periphery of that matrix on either side. Could be the top, the column margin or the row margin. Okay. Then basically just more examples of using apply. You can get the quantile, and then there you're saying the probabilities here of using the quantile. So this argument gets passed to quantile, hence the use of ... in the definition here. So notice that this arguments will go passed on to the quantile function. You can look up the quantile function and see what it does and see what the value changes. Here we're creating an array and we're applying. So here the margins are in fact a vector 1 and 2. And you can see how that will change. You're calculating the mean on those margins. It's not a matrix. It's just an example of how apply can be used not just for matrices but also for arrays and other things. And then finally, the mapply. We covered this example in class. Mapply rep 1, 4, 4, 1. This is a noise function example. And this is some other advanced stuff where you're creating this function which takes 3 arguments, mu, sigma, and x, and you're returning the sum of x minus mu divided by sigma square. So that's and then you take that, and then you basically sum of that. Oh, this is a way of saying that when we're using mapply, we get the result that we want, as opposed to just doing this particular. If we just call the function on its own, we don't get the value that we want. Okay, all right. If you have any problems with this, first watch the videos that are there with this material. So there are videos for each particular function. So mapply has a video, sapply has a video, tapply has a video. They're very short, 3 2-minute videos. You can watch them, and then if you still don't follow, feel free to send me an email, and I'll be happy to clarify your doubt. Okay, so I think we'll end our session here.